Horses.
Okay, so Hess's law.
Sound like Brenneman.
Oh my God.
This is not Hess's suggestions or Hess's theory. Okay, this is a
Hess had
law.
an idea once.
Which means that it is very.
Hess had a dream.
One day that there were students everywhere.
Will be judged by the color of their skin.
Whoa.
No, that's not what he said.
Judged by the equation that he gives. Whatever you do. And if they can do his equation or not.
Cohen? Cohen, if you're real smart, you're gonna shut up.
Not by the color of their skin.
Okay?
No matter how smart they are.
All right. So don't worry about the definition of this. It's more of an application kind of thing. So basically what it says is that, and this makes sense once you begin to see how it plays out. But what we're going to be talking about tomorrow is what's known as the enthalpy of formation. So basically what happens in the enthalpy of formation is how much energy is released in the production of a particular compound. Like, for example, water. So water is obviously, if you make water from hydrogen and oxygen, it's a very exothermic reaction. You see the flash, you see all this good stuff, okay? Very exothermic. Some reactions are endothermic. But what this is saying is that if you look at reactions and you add them together, and you all have done this, you've done a version of this already. When we did the half reactions, when we did redox reactions, okay? Oh, here's my reduction, here's my oxidation. And you, let's say, for example, you needed to get 10 electrons as the least common multiple. You might multiply 1 by 2, one equation by a factor of 2 and the other one by a factor of 5 to get things to cancel out. So Hess's law is a similar type thing, except we're going to apply it for thermodynamics. So there's a similarity to what you've already done. So like if you harken back to redox reactions,
It's all gone.
and like Ag plus 1 electron turns into Ag, and that's 0.80 volts, okay? Now, here's what's different. That is not 0.80 volts per mole. That's just 0.80 volts. So no matter how much silver you have, that number is always going to be the same. But what is similar is that if you reverse this and you turn that into an oxidation, what do you do with the sign? That now becomes negative 0.80 volts. So if it's positive in one direction, if you reverse the reaction, it becomes negative. Same thing is going to be true of your delta H values. So if you have a reaction the way it is written, and it's a negative value, it's an exothermic reaction the way it is written, if you reverse it and you change the sign, hey, that's going to become an endothermic reaction and delta H is going to change signs. Okay, so that part's the same. If you reverse it, you switch the sign. But what's different is that if, let's say that I needed 5 electrons to balance this out, and I multiplied that by 5, all I did was multiply the coefficients by 5. I didn't take 0.80 volts and multiply that by 5 and get 4.0, because that 0.80 was volts. It's an intrinsic property. It is not volts per mole. But if you look at thermodynamic values, and you can use Hess's law, we're going to use it for enthalpy today. You can use it for Gibbs free energy, you can use it for entropy, you can use it for anything that is based upon a thermodynamic value based upon kilojoules or joules per mole. Okay, so the other thing that you'll hear me say again and again about Hess's law when you work these problems is that this is a process, okay? It is not an answer. It is showing what you do to the equations. Do you reverse it? Do you multiply by half? Do you multiply by 4? Do you multiply by 2? Whatever you do. So the whole point of this is that you're going to show, hey, how does this work? So let me show you, we'll start off with a simple example. So you can take elemental copper plus oxygen, and you can get CO2, and that delta H is negative 393.5 kilojoules per mole. Carbon. And then you take carbon monoxide as a gas, react that with 1/2 O2 as a gas, and get carbon dioxide, and that delta H is negative 283.0 kilojoules per mole. Okay, so let me kind of show you the differences and the similarities in these two reactions. First off, both of them produce carbon dioxide, okay? You all right now cellularly are producing carbon dioxide. You all exhale carbon dioxide.
I was just proving your point. I don't know.
No, you were being annoying.
KSU.
You could have breathed without going,
Say it's a medical problem.
So, here's the difference between these two. This is the formation of carbon dioxide from its elemental form, okay? It's called standard enthalpy of formation. You make it from carbon and oxygen to produce carbon dioxide. So that's one way to produce carbon dioxide. It's a very exothermic reaction, negative 393.5. That's releasing a lot of energy. Now, the other way that you can make carbon dioxide is you basically, in effect, burn carbon monoxide in oxygen to produce CO2. Now, at this point, some of you are going to flip out and go, oh, Mr. Burkamp, this is bad. We have a 1/2, okay? We can't have half of an oxygen molecule. We have to have the whole thing. But the reason that that 1/2 is there is because if you were to balance it in the normal sense of being balanced, you would have a 2 here, you would have nothing in front of the oxygen, and you would have a 2 over there in front of the CO2. This is still balanced, but the reason that it's written with the 1/2 is that typically when you do thermodynamic equations, you want the product to have a coefficient of 1. So the normal balanced equations, you would have a 2 here, nothing there, and you would have a 2 there. So basically all we did is that we went in and we divided all of the coefficients by 2 to get the coefficient of the product have a value of 1, okay? So when you see thermodynamic stuff and you see fractions, don't flip out and go, oh, this is bad. No, it's just so that the coefficient is 1. Okay, so this is how this plays out. You're given some standard equations. So in this situation, here's what you have. You have these reactions. Now, the trick is, what do you do with them? So the next thing that you're given is that you're given another equation that you want to end up with. So what I want to do is determine I hate this pen.
Tell me the school wouldn't buy you a new iPad and pen for the $100,000 they.
You would think, wouldn't you? Okay. So you've got these two reactions. So what I want to know is that if I want to produce carbon monoxide, what should be the value of the thermodynamic of my delta H? Is it going to be an endothermic reaction? Is it going to be an exothermic reaction? So the beauty, and here's the practical side of Hess's law, is that if I know those reactions, and if I can arrange them in such a way that I end up with this, that means that I don't have to actually physically do the lab and come up with the value. I don't have to reinvent every wheel. So if I have a baseline of equations that I can use, I can rearrange those to come up with something that I don't have to reinvent the wheel on and do the experiment. So let's look at this. And it's a similar type process that you all have done before. First off, start with this. What's in there that you don't want that's in the first two reactions?
CO2.
CO2. I don't want CO2. So what does that mean? I've got to reverse one of the reactions, okay? One of them has to get reversed. Okay, cool, because I want the carbon. So part of this is not only what you want, it's what you don't want in the reaction. So I want to make the carbon dioxide go away. But in both of those, the carbon dioxide is a product. It's problematic. Okay, cool. But I want to get rid of one of them. Where do you want the carbon monoxide to go? As a product. So right away, if I reverse this one, and again, this is a process. You're going to go through and you're going to say, you're going to show me what you're doing, okay? This is not just write down the equations, a miracle happens, and I get the equation, okay?
Dang it.
You are showing the process. This is not miracles, okay? So let's do this. Let's just kind of go through this in steps and say, okay, well, let's just say we want to keep the first one as it is. Okay, I got carbon plus oxygen yielding CO2. I didn't do anything with that, so I got that as negative 3.5. And you're saying, hey, let's switch the bottom one. Cool, okay? So that becomes CO2
Hello. Hi, Joel. Oh, let her know. All right.
You can go. In case you didn't know. I know. Now I'm annoyed at you.
At least I showed up for your
Oh, and I
class.
appreciate that.
Unlike the others.
Yeah,
Leaving
like
me
some
all-
people I know.
Leaving me all alone. See you
You
guys?
skipped the first
I
half
know.
today? And then just shut up?
I'm just leaving for 4 o'clock.
Now, what are you gonna do with that delta H? Charles?
I don't know. Oh, flip the sign.
Yes. So now that
Yeah,
becomes
fine.
positive 283.0.
So why is he calling on me?
So, here's the story. So this is what you have to keep your eye on the prize. Where do you want to end up? So in this situation, my CO2s will cancel out. That goes away. I've got an oxygen on one side. I have a half of an oxygen on the other. So that's going to add up to leave me a net of 1/2. So I got carbon plus 1/2 O2 is going to get me CO.
Then add me a flip the sign.
That's what you want, okay? So what this means is that if you want to make carbon monoxide, and there's a whole bunch of different ways you can make carbon monoxide, but if you want to make it from its elemental form, and again, now we don't have to do the reaction. So if you take somebody take the calculator, Christmas, do you a favor, take negative 393.5 and add that to 283.0.
Negative 110.5.
So if you were to make carbon monoxide by burning elemental carbon, like let's say you have charcoal, which is basically elemental carbon, and you burn it in the presence of oxygen to produce carbon monoxide, is that an endothermic or exothermic reaction?
So,
Exothermic. So this would have a net release of energy. So then what you could do is you say, ooh, is Hess's law correct? So then if you know that, then you could actually run the reaction, see if the delta H actually matches that value. If it does, hey, cool. If it's not, there's something wrong somewhere. Now, that's as simple as it gets. A little bit more complicated, but it's the same process. Now I'm gonna have 3 reactions.
Bruce is in my comments. 8 reactions. Figure it out. Ghost.
Okay, so here's what you've got in your carbon. Okay. So there's some subtle things about what you have. One is that, notice that this says liquid water. So once you begin to actually look at the thermodynamic properties of water, you have 2 different sets of data. You have data for water as a gas, and you have data for water as a liquid. They are not the same, okay? So when you begin to actually, there's a whole table of thermodynamic data that we're going to get into tomorrow. This is in the back of your book, okay? That thermodynamic data, when you look at water, there's a vast difference between water as a liquid versus water as a gas. So this is why it's important on this one, when I did that I put that L on the end, because those are vastly different data. Okay, that's the significance of that. So here's what you got. Basically, one way to produce carbon dioxide, elemental carbon plus oxygen to produce carbon dioxide. Now, the second one, you're just blowing up oxygen in the presence of hydrogen, and you're going to get water. You all were used to seeing that as 2H2 plus O2 yielding 2H2. That's the normal version you're used to seeing. But this is thermo. We want the water to have a coefficient of 1. It's not a new equation. It's like, oh, we've never seen that. It's just burning hydrogen and oxygen to make water. This one, now, you're going to burn methane, CH4, which is typically, like, for example, when you guys light the Bunsen burners, right? That's, it might be propane, it might be methane, it's one of the natural gases. Now, out of any combustion reaction with a hydrocarbon, what do you get?
Heat, water.
Carbon dioxide and
Water.
water. This is why when you all right now, you are little combustion reactions. Do not breathe out loud, so help me, Cohen. So when you breathe out, you're breathing out 2 things from the combustion process on a cellular level. You're breathing out water vapor, and you're breathing out carbon dioxide, okay? Now, how can you prove that you're breathing out water vapor?
Breathe
Outside
in
was
glass.
If it's cold, what happens?
Breath
Fogs.
Well, it condenses, right? You get, ooh, look, you know, bits of steam condensing into a little cloud if it's cold outside. That's just the warm vapor that you're expelling, and it's coming out as a vapor. So here's the big idea. I want to get down to the production of methane. I want to make this from 1 carbon atom and 2 hydrogens. So what I want to know is if I want to make methane from that equation, I want to take oxygen or hydrogen plus carbon and make CH4. So, Sydney, right away, what are you going to have to do with that 3rd equation?
Flip it.
So I know I'm going to have to flip this, okay? Now, You might have to flip it and multiply by 2. You might have to flip it and divide by 3. You might have to flip it and just leave it, okay? So don't think, oh, we can only do one thing, okay? No. You can flip, multiply, divide. There isn't just, it isn't like you only get one thing and then you're done, okay? No. So let's start with this. So Sydney says she wants to flip that one. So I'm going to rewrite that as CO2 plus H2O liquid yielding CH4 plus 2O2. Now, what about the C plus O2 yielding CO2? Leave that now. Here's important. I'm going to flip this one, so this is going to become a positive 890.3. So, look at what you want to get rid of. So right away, you've got oxygens. You don't want oxygens. So you want to make the oxygens go away. So I've got 2 oxygens over here. Well, I've got my C plus O2 yielding CO2. So I want to make, there's a couple of things that I want to make disappear. I want to make the carbon dioxide disappear, and I want to make the oxygen disappear. So 2 things I have to get gone. Carbon dioxide and the oxygen. And the water. So what can I do? Sean.
I mean, the first one produces CO2, so you can.
What'd you say?
The first one produces CO2, so you can use that to cancel out the first CO2.
But you're going to want to work this all together. Let me give you a hint.
Reverse the second one.
You want to reverse the second one.
No. Multiply by 2. Multiply by 2.
Multiply by
Cancel out the
2.
H2O.
Okay.
Yeah.
So then I got 2H2. Right? And then that becomes negative 571.6. All right? Now, it's possible that you don't do anything to the equation. For now, I'm just going to leave the top equation as it is. So I'm going to get carbon plus O2 yielding CO2. And that's negative 393.4. If we do nothing else, okay, let's just try this, because sometimes it's just trial and error. You try it, see if it works. So right away, is my carbon dioxide going to go away?
Yes.
Because I've got one here, I've got one there. My carbon dioxides are gone. What about my O2s? Because I got 2 O2s there, and I've got an O2 there and an O2 there. Those are gone. Cool. Now, what else you got?
Water.
Waters. Okay? So I've got a water up there and a water there. Hold on. But now I've got my carbon, right? And I've got my hydrogens. So, let me make sure I wrote everything down here. Hold on, I left out a coefficient somewhere. Give me a second. I gotta figure out where I dropped numbers. Because that should cancel everything out.
In the last equation.
Oh, that should be a 2 in there. That's where we went south. I left out that 2. That should be 2 waters. That's where you pay attention to the little things. Then that all drops out, and then when you add all that up together, you just get the C plus 2H2 yielding, it's like, man, I broke physics. So when you add all this up, you get negative 74.8. Now, when you're adding these, almost all of these numbers are out to the tenth place, and if you remember your rules of significant digits, if they're to the tenth place, you keep that place value. So if you do this, like, don't round that to negative 75. Keep that out to the tenth place. So what this says is that if you take pure carbon and burn it in hydrogen to make CH4, that's going to be an exothermic reaction, negative 74.8. So what that means is once I get this number, I don't, again, the whole point of this is that you don't have to go through and run the reaction. Oh, if I've got this baseline of knowledge, I can just manipulate them and figure out what the reaction's going to be. Okay, I am done.
Yeah, you should just shut it off. Don't let them get to see it.
No, because then they're going to come in tomorrow and whine about it, and then I've got to write it down for each one of them and no.
Just, this is just a prank, right? This is just for them.
Like, no, because they update their phone. It stops it for like 45 minutes.
Oh, is this like,
PG.
like the beginning of the book?
Has a jump 9 to 52.
No, no.
Okay, so 63 through 66, those are the only ones that are Hess's laws, right? But again, I beg of you, when you do these Hess's laws, what I would recommend is that you write out the original equations as they are. Then figure out what you need to do. The idea is that this is a process. You are showing me what you did. So if you reverse a reaction, put an arrow that says, hey, this one got flipped. Maybe you divide by 2. Maybe you multiply by a third. Maybe you multiply by pi. I don't care. Okay, if you multiply by pi, something's really weird. But the idea being is that you are trying to show me what you did to end up with the equations. Okay? Magic does not work. Okay? So just don't write out the initial set of equations and go, oh, look, I ended up with the correct form. How cool is that? No, bad. When you get to question 7C, and this will make sense once you get to 7C, just answer the first question on that, okay? It'll make sense. It's weird now, but it'll make sense. A lot of this is thermodynamic stuff, okay? The delta E and Q and W, okay? So when you do 53, that's Q equals M delta T, C sub P, so just keep that in mind. So, all right, I'm done. You're on your own. Slackers.